The universe is vast, so vast that even with all our advancements in science and technology, we've barely scratched the surface of understanding it. Out there, beyond the reach of our telescopes and probes, lie mysteries that defy explanation, questions that challenge everything we think we know. From strange signals echoing across the cosmos to objects that seem to break the very laws of physics, these enigmas remind us just how much we still have to learn. And that's what makes them so fascinating. Today, we're diving into 22 of the most baffling space mysteries that continue to stump scientists and ignite our imaginations. These aren't just puzzles for astronomers, they're gateways to a deeper understanding of the universe, and maybe even our place within it. So, let's take a journey into the unknown and explore the phenomena that keep us looking up at the stars, wondering what secrets they hold. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars and planets. Statistically, it seems almost impossible that we're alone. Yet here we are, gazing at the stars and asking one of the most profound questions in science: where is everyone? This is the heart of the Fermi Paradox, named after physicist Enrico Fermi, who famously posed the question during a casual conversation in the 1950s. If the universe is so teeming with potential for life, why haven't we found any evidence of it? To tackle this mystery, scientists often turn to the Drake equation, a fascinating formula created by astronomer Frank Drake in the 1960s. It's not a traditional equation with a single answer, but rather a way to estimate the number of detectable civilizations in our galaxy. The equation considers factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life developing on those planets. But here's the catch: almost every variable in the Drake equation is filled with uncertainty. We simply don't have enough data to pin down exact numbers, which leaves the question of extraterrestrial life wide open. This uncertainty has led to some intriguing theories, one of the most thought-provoking being the Great Filter. The idea is that somewhere along the path from simple organisms to advanced spacefaring civilizations, there's a barrier, a filter, that prevents most life from progressing. The terrifying question is, where is this filter? Is it behind us, meaning life is extraordinarily rare to begin with? Or is it ahead of us, suggesting that advanced civilizations inevitably destroy themselves before they can make contact? Either way, the implication for humanity is profound. Are we the exception, or are we destined to face the same fate? Experts like astrophysicist Carl Sagan have pondered this, emphasizing the fragility of intelligent life. Sagan once said, "The universe seems neither benign nor hostile, merely indifferent." This indifference is part of what makes the Fermi Paradox so haunting. We're left to wonder if the silence of the cosmos is a sign of our uniqueness or our doom. As we grapple with these questions, it's worth noting that the search for extraterrestrial life is far from over. Projects like SETI, the search for extraterrestrial intelligence, continue to scan the skies for signals, while missions to Mars and beyond aim to uncover even microbial life. But for now, the Fermi Paradox remains one of the most compelling mysteries in space science, a reminder of how much we still have to learn about the universe and ourselves. And speaking of mysteries, the cosmos holds another enigma that's equally baffling, one that makes up the majority of the universe's mass yet remains invisible to us. That's right. Next, we'll dive into the shadowy world of dark matter, a puzzle that challenges our understanding of physics and the very fabric of reality. But that's a story for the next mystery. But as we peel back the layers of the universe, we stumble upon something even more baffling: dark matter. Unlike the stars and galaxies we can see, dark matter doesn't emit, absorb, or reflect light. It's completely invisible, yet its presence is undeniable. Think of it like the wind. You can't see it, but you can feel its effects. In this case, its gravitational pull shapes the very structure of the cosmos. Without dark matter, galaxies as we know them wouldn't exist. they'd fly apart, unable to hold themselves together. So, what exactly is dark matter? Honestly, we don't fully know, and that's what makes it one of the greatest mysteries of modern science. Physicists estimate it makes up about 27% of the universe, while the ordinary matter we're familiar with, planets, stars, and even us, accounts for less than 5%. The rest, that's another mystery we'll get to shortly. Scientists have proposed countless theories, from exotic particles to hidden dimensions, but none have been proven yet. Experiments like the Large Hadron Collider are hunting for clues, smashing particles together at incredible speeds in hopes of detecting even a faint trace of dark matter. Meanwhile, astronomers observe its gravitational fingerprints, watching how it bends light from distant galaxies in a phenomenon called gravitational lensing. The hunt for dark matter isn't just about solving a cosmic puzzle, it's about understanding the very fabric of our universe. And while we're still searching, one thing is clear: the answers we find could redefine everything we know about space, time, and existence itself. Which brings us to another mystery, equally perplexing and perhaps even more influential: dark energy. Have you ever wondered what's pushing the universe to expand faster and faster, almost like it's in a cosmic hurry? This brings us to the third mystery on our list: dark energy. This invisible force, which makes up about 68% of the universe, is the driving engine behind the accelerated expansion of our cosmos. But here's the twist: despite its overwhelming presence, we know almost nothing about what it actually is. The story of dark energy's discovery begins in the late 1990s, when astronomers studying distant supernova made a shocking observation. They found that the universe wasn't just expanding, it was expanding at an ever-increasing rate. This was completely unexpected, as scientists had assumed gravity would eventually slow everything down. Instead, something was counteracting gravity's pull, pushing galaxies apart at a faster and faster pace. That something is what we now call dark energy. But what exactly is it? That's where things get tricky. Dark energy doesn't behave like anything we've encountered before. It's not matter, it's not radiation, and it doesn't interact with light or any other form of electromagnetic energy. Imagine trying to study something that's completely invisible, silent, and intangible, yet it's shaping the fate of the entire universe. That's the challenge physicists face today. To put it in simpler terms, think of the universe as a balloon being inflated. Dark energy is like the air inside, causing the balloon to expand faster and faster. But unlike air, we have no way to measure or detect dark energy directly. It's a cosmic enigma that defies our current understanding of physics, and it's forcing scientists to rethink the fundamental laws that govern reality. The implications of dark energy are staggering. If it continues to drive the universe's expansion, it could lead to a future where galaxies are so far apart that the night sky becomes eerily empty. Stars would fade from view, and the universe would grow colder and darker over billions of years. It's a chilling thought, but one that underscores just how little we know about this mysterious force. And speaking of mysteries, dark energy isn't the only cosmic puzzle that leaves scientists scratching their heads. Up next, we'll explore another phenomenon that's equally baffling: black holes. These cosmic vacuum cleaners are not just strange, they're gateways to some of the most extreme physics in the universe. But that's a story for the next mystery. Now, let's turn our attention to one of the most perplexing puzzles in modern physics: the black hole information paradox. Imagine tossing a book into a fire. The pages burn, the ink fades, but in theory, if you could collect every particle of smoke, ash, and light emitted, you might reconstruct the book. The information in some form would still exist. But what happens when something or someone crosses the event horizon of a black hole? According to classical physics, everything that falls into a black hole is lost forever, crushed into the singularity at its core. But here's the twist: quantum mechanics insists that information can never be destroyed. So, where does it go? This paradox has puzzled scientists for decades, and one of the most influential voices in this debate was Stephen Hawking. He proposed that black holes aren't entirely black, they emit radiation, now famously known as Hawking radiation. Over time, this radiation causes black holes to lose mass and eventually evaporate. But if the black hole disappears, what happens to all the information it swallowed? Hawking initially suggested that the information might be irretrievably lost, a conclusion that sent shockwaves through the physics community because it directly contradicted the principles of quantum mechanics. The debate has only intensified since then. Some physicists argue that the information is encoded in the Hawking radiation itself, scrambled beyond recognition but still present. Others propose that it might be stored in a mysterious, holographic form on the black hole's event horizon. And then there are those who suggest that the information escapes into a parallel universe, a concept that sounds more like science fiction than science, but in the world of theoretical physics, sometimes the truth is stranger than fiction. To help visualize this, think of a black hole like a cosmic blender. When you blend a smoothie, the fruits and liquids are mixed so thoroughly that they're unrecognizable, but they're still there, just in a different form. The question is, can we unblend the smoothie, or is the information truly lost forever? This paradox isn't just a philosophical debate, it's a fundamental challenge to our understanding of reality. If we can solve it, we might unlock the secrets of how the universe works at its deepest levels. But the mystery of black holes is just the tip of the cosmic iceberg. As we peel back the layers of the universe, we encounter another enigma that challenges our understanding even further: quasars. These dazzling, distant objects are some of the brightest and most energetic phenomena in the cosmos, and their strange behavior continues to baffle astronomers. What powers these cosmic lighthouses, and why do they behave in such unpredictable ways? Let's dive into that next. Picture this, an object so bright, it outshines entire galaxies, yet it's no larger than our solar system. This isn't science fiction, it's a quasar, one of the most enigmatic and dazzling phenomena in the cosmos. Quasars, short for quasi-stellar radio sources, are the brightest objects in the universe, capable of emitting energy thousands of times more than an entire galaxy. But where does this incredible power come from? The answer lies in the heart of these cosmic giants, supermassive black holes. As matter spirals into these black holes at incredible speeds, it heats up to extreme temperatures, releasing vast amounts of energy in the form of light and radiation. This process makes quasars visible across billions of light years, acting as beacons from the early universe. But quasars aren't just cosmic curiosities, they play a crucial role in the evolution of galaxies. Scientists believe that quasars, in their youth, may have helped shape the galaxies we see today. The immense energy they release can drive away gas and dust, halting star formation and influencing the growth of their host galaxies. This makes quasars not only fascinating to study, but also key to understanding how galaxies form and evolve over time. Yet, studying them is no easy task. Quasars are incredibly distant, often located billions of light years away, which means we're seeing them as they were billions of years ago. This distance makes it challenging to gather detailed data, but advancements in telescopes and observational techniques are slowly peeling back the layers of their mystery. Historically, quasars were first discovered in the 1950s and 60s, initially mistaken for stars due to their point-like appearance. It wasn't until later that astronomers realized these objects were something entirely different. Fast forward to today, and we've made significant strides in understanding quasars, thanks to missions like the Hubble Space Telescope and the James Webb Space Telescope. Recent discoveries have revealed that quasars were more common in the early universe, suggesting they played a pivotal role during the cosmos' formative years. As we continue to study these luminous giants, they offer us a window into the universe's past and the forces that shaped it. Now, while quasars illuminate the distant reaches of space, there's another mystery that takes us even further back in time, right to the very beginning of the universe itself. That mystery is the cosmic microwave background radiation, the faint afterglow of the Big Bang. But we'll explore that in just a moment. Imagine looking back in time, not with a telescope, but by observing the faint glow of light that has traveled across the universe for over 13 billion years. This is the cosmic microwave background, or CMB, a snapshot of the universe just 380,000 years after the Big Bang. Think of it as the ancient echo of creation, a map of the cosmos in its infancy, still imprinted on the fabric of space itself. The CMB is more than just a relic, it's a treasure trove of information, revealing the universe's earliest moments and the seeds of everything we see today. But here's where things get intriguing. While the CMB fits remarkably well with our understanding of the Big Bang and the expansion of the universe, it also holds puzzling anomalies that defy our expectations. For instance, one of the most baffling features is the so-called cold spot. This region of the CMB is significantly colder than the surrounding areas, and its existence challenges our standard cosmological models. Scientists have proposed everything from cosmic voids to parallel universes as potential explanations, but the truth remains elusive. Another anomaly is the unexpected alignment of certain patterns in the CMB, which some researchers suggest could hint at a larger, unseen structure influencing the universe on a grand scale. These anomalies aren't just curiosities, they're clues. They push us to rethink our understanding of the cosmos and question whether our current models are truly complete. As we continue to study the CMB with increasingly precise instruments, we may uncover even more surprises that reshape our view of the universe's origins and evolution. And speaking of unseen structures, this brings us to another cosmic enigma, one that lies much closer to home, yet remains shrouded in mystery: the Great Attractor. What is this invisible force pulling entire galaxies, including our own, toward it with irresistible power? Let's dive into that next. Hidden in the depths of our universe lies a force so powerful that it's pulling entire galaxies toward it, like a cosmic magnet we can't fully see or understand. This is the Great Attractor, a gravitational anomaly that has puzzled scientists for decades. Located roughly 250 million light-years away in the direction of the constellations Centaurus and Norma, it's pulling not just our Milky Way, but thousands of other galaxies toward it at incredible speeds. But here's the catch: we can't directly observe it. Why? Because it's hidden behind the dense plane of our own galaxy, obscured by stars, gas, and dust. It's like trying to spot a lighthouse through a thick fog. You know it's there, but you can't quite see it clearly. The Great Attractor's immense gravitational pull suggests it's a massive concentration of matter, possibly a supercluster of galaxies or something even more mysterious. Some scientists speculate it could be part of an even larger structure, like the Laniakea supercluster, which encompasses thousands of galaxies, including our own. Renowned astrophysicist Alan Dressler once described it as a gravitational focal point in our cosmic neighborhood, emphasizing its role in shaping the large-scale structure of the universe. But despite its significance, the Great Attractor remains one of the most elusive enigmas in modern astronomy. Every observation we make is like piecing together a puzzle with half the pieces missing. So, what does this mean for our understanding of the cosmos? The Great Attractor challenges our assumptions about the distribution of matter and the forces shaping the universe. It's a reminder that even in an era of advanced telescopes and space probes, there are still colossal mysteries lurking just beyond our reach. And speaking of mysteries that defy explanation, let's turn our attention to another cosmic puzzle: fast radio bursts. These fleeting, high-energy signals from deep space have left scientists scratching their heads for years. What could be causing them, and what do they tell us about the universe we're still learning to understand? One of the most baffling phenomena in modern astronomy is the existence of fast radio bursts, or FRB. These are incredibly brief but staggeringly powerful bursts of radio waves that flash across the cosmos in just milliseconds. Despite lasting less than the blink of an eye, they release as much energy as the sun does in days. And here's the kicker: we still don't fully understand where they come from or what causes them. FRBs were first detected in 2007, and since then, astronomers have catalogued hundreds of these mysterious signals. They seem to originate from deep space, far beyond our galaxy, and their sporadic nature makes them incredibly hard to predict or study. Some FRBs are one-time events, while others repeat at irregular intervals, adding another layer of intrigue to their already puzzling nature. One leading theory suggests that FRBs might be linked to neutron stars, extremely dense remnants of collapsed stars. Specifically, a type of highly magnetized neutron star called a magnetar could be responsible. When these cosmic powerhouses undergo sudden shifts or starquakes, they might release these intense bursts of energy. But not all scientists are convinced. Another, more speculative idea is that FRBs could be evidence of advanced extraterrestrial civilizations. Could these bursts be some form of interstellar communication or even propulsion signals? While this theory is far from proven, it's a tantalizing possibility that keeps the mystery alive. Recent discoveries have only deepened the enigma. In 2020, astronomers detected an FRB originating from within our own Milky Way galaxy, marking the first time one was observed so close to home. This discovery provided crucial data, but it also raised new questions. Why do some FRBs repeat while others vanish forever? And why do their signals vary so dramatically in strength and structure? Each answer seems to lead to more questions, keeping FRBs firmly in the realm of cosmic mysteries. As we continue to search for answers about fast radio bursts, another intriguing object beckons for our attention. A visitor from beyond our solar system that has sparked its own share of debates and theories. This brings us to our next mystery, the strange, cigar-shaped object known as Oumuamua. Now, let's turn our attention to one of the most intriguing cosmic visitors in recent history, Oumuamua. Discovered in October 2017, this interstellar object zipped through our solar system, leaving scientists baffled by its strange behavior. Unlike typical asteroids or comets, Oumuamua had an elongated, cigar-like shape, something almost unheard of in natural space debris. But what really set it apart was its unexpected acceleration as it moved away from the sun. Instead of slowing down, it sped up, defying the laws of gravity as we understand them. This bizarre behavior sparked a flurry of theories. Some astronomers suggested it could be a fragment of a larger object, perhaps shattered by a cosmic collision. Others proposed it might be a hydrogen iceberg, a type of object never before observed. But the most controversial idea came from Harvard astrophysicist Avi Loeb, who speculated that Oumuamua could be an artificial object, perhaps a piece of alien technology, like a light sail propelled by solar radiation. While this theory remains hotly debated, it's a fascinating reminder of how much we still have to learn about the universe. What's undeniable is that Oumuamua opened our eyes to the possibility of otherworldly visitors. Its brief visit left us with more questions than answers, challenging our assumptions about what's out there. And as we ponder the mysteries of this interstellar traveler, we're reminded that the cosmos is full of surprises, some of which might be closer than we think. Speaking of surprises, our next mystery takes us from the realm of physical objects to something even more elusive, a signal from deep space that has puzzled scientists for decades. But more on that in just a moment. Now, let's turn our attention to one of the most tantalizing mysteries in the search for extraterrestrial intelligence, the WOW signal. Back in 1977, a radio telescope at Ohio State University picked up something extraordinary, a signal so powerful and unusual that it left astronomers stunned. Lasting just 72 seconds, the signal was so significant that the scientist who discovered it, Jerry Amon, circled the data on the printout and wrote, "Wow" next to it, and that's how it got its name. What made the "wow" signal so remarkable? It wasn't just its strength. The signal appeared to come from a specific point in space near the constellation Sagittarius, and it matched the exact frequency that scientists had predicted an extraterrestrial civilization might use to communicate. This frequency, known as the hydrogen line, is a natural choice for interstellar communication because hydrogen is the most abundant element in the universe. But here's the kicker: despite decades of searching, the signal was never detected again. So, where did it come from? Some believe it could have been a natural phenomenon, like a comet or a distant star emitting an unusual burst of energy. But others argue that its precise characteristics make it a strong candidate for an intentional signal from an advanced civilization. The mystery deepens when you consider how difficult it is to replicate such a brief, intense burst of energy without any apparent natural source. The WOW signal remains one of the most compelling pieces of evidence in the search for extraterrestrial life, not just because of its uniqueness, but because it challenges our understanding of what's out there. Even today, scientists continue to investigate similar signals, hoping to find another clue that might bring us closer to answering one of humanity's oldest questions: are we alone? And speaking of mysteries that challenge our understanding of the cosmos, let's shift our focus to another enigma that's equally fascinating: rogue planets. These are worlds that don't orbit any star, drifting freely through the vast emptiness of space. What makes them so intriguing, and how do they even exist? That's a story for the next mystery. Picture a world adrift in the vast emptiness of space, untethered from the warmth of a star, wandering endlessly through the cosmic void. These are rogue planets, lonely, free-floating worlds that have no star to call home. Unlike the planets in our solar system, which orbit the sun, rogue planets are nomads drifting through the galaxy on their own. But how do these orphaned worlds come to be? Scientists believe they might form in one of two ways. Either they're ejected from their home star system during chaotic gravitational interactions, or they form independently in the cold, dark regions of space, never bound to a star in the first place. Detecting these wandering worlds is no easy task. Without a star's light to illuminate them, rogue planets are incredibly difficult to spot. Astronomers often rely on a technique called microlensing, where the planet's gravity briefly bends the light from a distant star, creating a telltale flicker. Even with this method, only a handful of rogue planets have been confirmed so far. But recent discoveries have sparked excitement, like the detection of a rogue planet roughly the size of Earth, floating freely in our galactic neighborhood. Imagine the possibilities. Could these dark, untethered worlds harbor life, deep beneath icy surfaces or within hidden oceans? Rogue planets remind us just how dynamic and unpredictable the universe can be. They challenge our understanding of planetary formation and offer a glimpse into the countless unseen wonders drifting in the darkness. And speaking of unseen wonders, our journey through space's mysteries leads us next to the edge of our solar system, where the Kuiper Belt holds secrets of its own. Beyond the orbit of Neptune lies a vast, icy frontier that has captured the curiosity of astronomers for decades: the Kuiper Belt. This region, stretching billions of miles from the Sun, is home to countless icy bodies, some of which are remnants from the solar system's earliest days. Think of it as a cosmic freezer, preserving clues about how our planetary neighborhood came to be. But the Kuiper Belt isn't just a relic of the past, it's also a source of ongoing mysteries that challenge our understanding of the cosmos. One of the most intriguing aspects of the Kuiper Belt is its role in reshaping our knowledge of the solar system's formation. Scientists believe that the objects here, like Pluto and its smaller cousins, are essentially time capsules. By studying their composition and orbits, researchers can piece together how planets like Neptune and Uranus came to be and why they ended up in their current positions. But the Kuiper Belt doesn't just answer questions, it raises them too. For instance, the peculiar orbits of some distant objects suggest the presence of a hidden giant, often referred to as Planet 9. This hypothetical world, if it exists, could be 10 times the mass of Earth, lurking in the outer darkness and subtly tugging on these icy bodies. Yet, despite extensive searches, Planet 9 remains elusive, leaving us to wonder if it's out there at all. The Kuiper Belt also challenges our assumptions about the boundaries of the solar system. While we once thought Pluto marked the edge, we now know there's much more to explore. Missions like New Horizons have given us stunning close-ups of objects like Arakoth, a snowman-shaped world that offers a glimpse into the building blocks of planets. But with every discovery comes more questions. How did these objects form? Why do some have such unusual shapes? And what other secrets might be hiding in this distant, frozen expanse? As we peer into the Kuiper Belt, it's clear that this region is far more than a collection of icy rocks. It's a window into the solar system's past and a puzzle that continues to intrigue scientists. And speaking of cosmic puzzles, our next mystery takes us even further into the depths of space, to a place where the laws of physics seem to bend. The enigmatic world of neutron stars. Now picture the aftermath of a star's dramatic death, a supernova explosion so powerful it outshines entire galaxies. What remains isn't just a void, but one of the universe's most bizarre and extreme objects, a neutron star. These cosmic remnants are so dense that just a teaspoon of their material would weigh billions of tons on Earth. To put that into perspective, it's like squeezing the entire mass of Mount Everest into a sugar cube. Neutron stars are born from the collapse of massive stars, and their core is so compressed that protons and electrons fuse into neutrons, giving them their name. But their strangeness doesn't stop there. Some neutron stars spin at mind-boggling speeds, completing hundreds of rotations every second. These fast-spinning neutron stars are called pulsars, and they emit beams of radiation that sweep across space like a cosmic lighthouse. When these beams point toward Earth, we detect them as regular pulses of light or radio waves, a phenomenon that has fascinated astronomers since their discovery in the late 1960s. Then there are magnetars, a type of neutron star with magnetic fields so intense they could strip the data from every credit card on Earth from thousands of miles away. These magnetic fields are trillions of times stronger than Earth's, creating an environment so extreme it defies our understanding of physics. Studying magnetars is like trying to decode the universe's most powerful and mysterious forces, but their unpredictability makes them incredibly challenging to observe. Despite their small size, only about 12 miles in diameter, neutron stars are laboratories for testing the laws of physics under conditions we can't replicate on Earth. Their extreme density and gravity warp space-time, offering clues about how matter behaves under such intense pressure. Yet, for all we've learned, neutron stars still hold secrets that baffle scientists. Why do some become pulsars while others evolve into magnetars? What happens to matter at their cores, where the pressure is so immense it might even form exotic states of matter we've never seen before? As we peel back the layers of these enigmatic objects, we're led to another cosmic puzzle, one that ties directly to the explosive power of neutron stars and their interactions. This brings us to our next mystery, gamma-ray bursts, the most energetic events in the universe, often linked to the birth or death of neutron stars. These bursts shine with such intensity that, for a brief moment, they outshine everything else in the cosmos. But what exactly causes them? That's a question we'll dive into next. Now, let's shift our gaze to one of the most explosive and enigmatic phenomena in the cosmos, gamma-ray bursts, or GRB. These are not your everyday cosmic fireworks. GRBs are the most energetic events ever observed in the universe, releasing more energy in a few seconds than our Sun will emit in its entire 10 billion-year lifetime. Just think about that for a moment, a single burst lasting mere moments, outshining entire galaxies. But what causes these colossal explosions? Scientists believe GRBs are born from some of the most violent events in the universe. One leading theory points to the collision of neutron stars, those incredibly dense remnants of dead stars. When two neutron stars spiral into each other, the resulting crash sends out a torrent of gamma rays, lighting up the cosmos like a cosmic beacon. Another possibility is hypernova, the explosive deaths of massive stars. Unlike regular supernova, hypernova are thought to be so powerful that they can rip apart the star in a way that triggers a gamma ray burst. Recent discoveries have only deepened the mystery. In 2017, astronomers detected both gravitational waves and gamma rays from the same event, a neutron star collision. This groundbreaking observation confirmed part of the theory but also opened new questions. Why do some neutron star collisions produce GRBs while others don't? And what exactly powers these bursts to such extraordinary levels of energy? As we grapple with these questions, GRBs remind us just how much we still have to learn about the universe's most extreme events. And speaking of extremes, this leads us to another cosmic puzzle, one that's the theoretical opposite of a black hole. What happens when we flip the script and explore the concept of white holes? Imagine a cosmic phenomenon so mysterious that it defies everything we know about black holes. Enter white holes' theoretical counterparts that, instead of pulling everything in, violently expel matter and energy outward. According to Einstein's theory of general relativity, white holes are mathematically possible, acting as the reverse of black holes. But here's the catch. While black holes have been observed through their effects on surrounding space, white holes remain entirely hypothetical. No one has ever detected one, and scientists aren't even sure if they can exist in our universe. So, why do white holes capture the imagination of physicists and space enthusiasts alike? Picture this. If a black hole is like a cosmic vacuum cleaner, sucking in everything that crosses its event horizon, a white hole would be the opposite, a cosmic fire hose, spewing out matter and energy with unstoppable force. Some theories suggest that white holes could be the other end of a black hole, connected by a theoretical tunnel through spacetime known as a wormhole. This idea ties into the broader concept of spacetime bridges, which we'll explore in the next mystery. But why haven't we found any evidence of white holes? One possibility is that they're incredibly unstable, collapsing almost instantly after forming. Another idea is that they exist in regions of the universe we simply can't observe yet. Or perhaps they're just a fascinating quirk of mathematics, a solution to Einstein's equations that doesn't translate into reality. Either way, white holes challenge our understanding of the cosmos, pushing us to think beyond what we can see and measure. As we ponder the enigma of white holes, it's hard not to wonder, could they hold the key to understanding the deepest mysteries of the universe? And if they do exist, what would their discovery mean for our understanding of spacetime, gravity, and the very fabric of reality? These questions lead us naturally into our next cosmic puzzle, wormholes, the hypothetical shortcuts through spacetime that could rewrite the rules of travel across the universe. Picture this, a cosmic shortcut, a tunnel carved through the very fabric of space and time, connecting two distant points in the universe in the blink of an eye. This isn't science fiction, it's the tantalizing concept of wormholes, a hypothetical phenomenon that has fascinated scientists and dreamers alike. Wormholes, often called Einstein-Rosen bridges after the physicists who first theorized them, are like cosmic doorways that could, in theory, allow us to traverse unimaginable distances in an instant. But how do they work, and could they truly exist? At their core, wormholes are solutions to the equations of general relativity, suggesting that spacetime could fold in on itself, creating a bridge between 2 points. Think of it like a piece of paper. If you fold it so that 2 points touch, you've essentially created a shortcut. Now, apply that idea to the vast expanse of the universe. A wormhole could connect 2 galaxies or even 2 universes, making interstellar travel a possibility, at least on paper. But here's the catch: wormholes are incredibly unstable. Even if they exist, they'd likely collapse the moment anything tried to pass through them. To keep a wormhole open, you'd need something called exotic matter, a hypothetical substance with negative energy that defies our current understanding of physics. As physicist Kip Thorne once put it, wormholes are like a highway with no exit ramps. They're fascinating to imagine, but practically impossible to navigate. And then there's the question of where they might lead. Could a wormhole take us to another galaxy, or even another universe entirely? Some theories suggest that wormholes might be gateways to alternate realities, sparking the imagination of scientists and storytellers alike. But for now, these ideas remain firmly in the realm of speculation, as no evidence of wormholes has ever been found. As we ponder the mysteries of wormholes and their potential to rewrite the rules of space travel, we're led to an even more profound question. Could these cosmic tunnels be connected to the existence of a multiverse? If wormholes are real, do they hint at a universe far more complex and interconnected than we ever imagined? Stay with us as we dive into the next mystery, the enigmatic nature of the multiverse, and explore whether our universe is just one of countless others. What if our universe is just one of countless others, each with its own set of physical laws and realities? This is the tantalizing idea behind the 17th mystery on our list, the multiverse. The multiverse theory suggests that our universe might be one of many, existing in a vast cosmic landscape where every possible outcome plays out somewhere. It's a concept that bridges physics and philosophy, offering a potential explanation for one of the most puzzling questions in science: why is our universe so finely tuned for life? The constants of nature, like the strength of gravity or the speed of light, seem perfectly calibrated to allow stars, planets, and ultimately life to exist. But why? Is it mere coincidence, or could the multiverse hold the answer? Imagine a cosmic lottery where every possible combination of physical laws exists in some universe. In most of these universes, the conditions might be too chaotic or inhospitable for life to form. But in a rare few, like ours, the numbers align just right. This idea, while speculative, has gained traction among scientists as a way to explain the apparent fine-tuning of our universe. Physicists like Max Tegmark and Brian Greene have explored the multiverse concept, suggesting that it could arise from the mathematics of quantum mechanics or the inflationary model of the Big Bang. But it's not just a scientific curiosity, it's a philosophical bombshell. If the multiverse is real, it challenges our understanding of existence itself. Are we just one version of reality among an infinite number? And if so, what does that mean for our place in the cosmos? Now, let's pivot from the vast, mind-bending scale of the multiverse to something equally mysterious but much smaller: the strange world of quantum entanglement. This phenomenon, often called spooky action at a distance by Einstein, is our next mystery, and it might just connect the dots between the cosmic and the quantum. Picture two particles separated by millions of light years, yet somehow still linked in a way that defies everything we know about space and time. This is quantum entanglement, one of the strangest and most baffling phenomena in the universe. When two particles become entangled, their properties become intertwined so that measuring one instantly affects the other, no matter how far apart they are. It's as if they're communicating faster than the speed of light, breaking one of Einstein's cardinal rules and leaving scientists scratching their heads. Einstein himself famously called it spooky action at a distance, and even he struggled to wrap his mind around it. But what does this mean for us? Well, imagine a pair of dice that always land on the same number, no matter how far apart you roll them. That's the kind of eerie connection we're talking about. This phenomenon isn't just a curiosity, it has real-world implications, especially in the realm of quantum communication. Researchers are exploring how entangled particles could revolutionize secure communication, creating networks that are virtually unhackable. But here's the catch: quantum entanglement challenges the very foundations of classical physics, forcing us to rethink what we know about reality itself. Now, as mind-bending as this is, it's just the tip of the cosmic iceberg. If quantum entanglement makes you question the nature of space and connection, wait until you hear about the next mystery, the holographic principle. Could our universe be a projection, a two-dimensional surface encoding all the information we perceive in 3 dimensions? It sounds like science fiction, but some of the brightest minds in physics are seriously considering this idea. And that's where we're headed next, into a mystery that might just change the way we see reality itself. Imagine if everything we see, touch, and experience, every star, every galaxy, even you and I, were nothing more than a projection, a cosmic illusion. This is the mind-bending idea behind the holographic principle, a theory that suggests our universe might be a hologram. But what does that even mean? Well, it all starts with a radical rethinking of how space and information work. According to this principle, the entire universe could be encoded on a two-dimensional surface, like a giant cosmic DVD, and what we perceive as three-dimensional reality is just an incredibly detailed projection of that information. The origins of this theory trace back to the work of physicists Gerard T. Hooft and Leonard Susskind in the 1990s. They proposed the idea while grappling with black holes and the perplexing question of what happens to information that falls into them. Black holes, as we know, are regions of space where gravity is so intense that not even light can escape. But if information can't be destroyed, as quantum mechanics suggests, then where does it go? The holographic principle offers a fascinating solution. The information isn't lost, it's stored on the boundary of the black hole, like data etched onto the surface of a sphere. This idea doesn't just apply to black holes. It implies that the entire universe might operate the same way. Think of it like this. If you've ever watched a hologram, you know it's a flat image that appears three-dimensional when light hits it just right. The holographic principle suggests that our universe might be a similar kind of illusion, with all the information about everything that exists, every particle, every force, every event encoded on a vast two-dimensional boundary at the edge of the cosmos. What does this mean for our understanding of reality? For one, it challenges the very nature of space and time. If the universe is a hologram, then the three-dimensional world we experience might be an emergent property of a deeper, more fundamental layer of reality. It also raises profound questions about free will, consciousness, and the nature of existence itself. Are we living in a simulated universe, or is this simply the way the cosmos organizes itself on the most fundamental level? While the holographic principle is still a theoretical framework, it has gained traction in the scientific community, particularly in the study of quantum gravity and string theory. Some researchers even suggest that experiments could one day test whether the universe truly operates like a hologram, using advanced particle accelerators or observations of the cosmic microwave background. But if the holographic principle leaves you questioning the very fabric of reality, just wait, because our next mystery takes us back to the very beginning of everything. What sparked the universe into existence? What lies beyond the Big Bang? These are the questions we'll explore as we dive into one of the most profound enigmas in all of science. The Big Bang. It's a term we've all heard, but what does it really mean? This monumental event is often described as the moment the universe burst into existence, an explosion of energy and matter that set the stage for everything we know. But here's the twist: the Big Bang isn't just the beginning of the universe, it's also one of its greatest mysteries. What caused it? What, if anything, existed before it? And how can we even begin to study something that happened over 13.8 billion years ago? Think of the Big Bang like a cosmic puzzle with half the pieces missing. Scientists have pieced together much of the story using clues like the cosmic microwave background, a faint glow of radiation left over from the early universe. But even with these clues, the Big Bang raises more questions than answers. For instance, if the universe expanded from an unimaginably hot and dense point, what triggered that expansion? Some theories suggest a quantum fluctuation, while others point to the collision of higher dimensional objects. The truth is, we're still searching for the spark that lit the cosmic fire. And then there's the ultimate question: what was there before the Big Bang? This is where things get truly mind-bending. Time, as we understand it, began with the Big Bang, so asking what happened before might not even make sense. It's like trying to find the edge of a sphere. It just doesn't exist in the way we're used to thinking. Some physicists propose that our universe is just one of many in a vast multiverse, while others suggest that time itself could be cyclical, with universes expanding and collapsing in an endless loop. Studying the Big Bang is no easy task. It's like trying to reconstruct the first chapter of a book when all you have are a few scattered sentences. Yet, the pursuit of understanding this event drives some of the most ambitious scientific projects in history, from particle accelerators probing the tiniest building blocks of matter to space telescopes capturing the faintest whispers of the early universe. Every discovery brings us closer to unraveling the mystery, but it also reminds us of how much we still don't know. As we ponder the origins of the universe, we're led to another profound question: what is time? If the Big Bang marked the beginning of time as we know it, then understanding its nature might hold the key to unlocking the deepest secrets of existence. And that's where our next mystery takes us, into the enigmatic fabric of time itself. Time. It's something we all experience, yet its true nature remains one of the most elusive mysteries in the cosmos. Think about it: seconds tick by, days turn into years, and yet, what is time really? Is it a river flowing in one direction, or could it be something far more complex? This is where the 21st mystery of our journey takes us, into the enigmatic nature of time itself. At its core, time is the framework that allows events to unfold in a sequence, from the birth of stars to the blink of an eye. But here's where it gets fascinating. According to Einstein's theory of relativity, time isn't a fixed universal constant. Instead, its relative, meaning it can stretch, slow down, or speed up depending on factors like gravity and velocity. Picture this: an astronaut traveling near the speed of light would age slower than someone on Earth. It's a mind-bending idea that challenges our everyday understanding of how time works. Then there's the quantum realm, where time seems to play by an entirely different set of rules. In the strange world of particles, time might not even flow in a straight line. Some physicists suggest it could be more like a network of interconnected moments, where the past, present, and future coexist in a tangled web. This raises questions: could time be an illusion, a construct of our perception? Or is it a fundamental property of the universe, woven into the fabric of reality itself? To explore these ideas, scientists often turn to thought experiments. One famous example is the twin paradox, where one twin travels through space at near light speed while the other stays on Earth. When they reunite, the traveling twin has aged less, a real-world consequence of time dilation. Another intriguing concept is the block universe theory, which suggests that all moments in time, past, present, and future, exist simultaneously, like frames in a film. What does all this mean for us? It challenges us to rethink our place in the universe and how we perceive reality. Time isn't just a backdrop to our lives. It's a dynamic, mysterious force that shapes everything from the smallest particles to the largest galaxies. And as we stand on the edge of this cosmic puzzle, it's impossible not to wonder what lies at the end of time itself. This brings us to the final mystery, a question that ties everything together. What is the ultimate fate of the universe? Does time have an end, or does it stretch into infinity? Join us as we explore this profound question, one that takes us to the very limits of human understanding. As we gaze into the vast expanse of the cosmos, one question looms larger than any other: how will it all end? The fate of the universe is one of the most profound mysteries in science, and while we may not have definitive answers, there are several compelling theories that attempt to unravel this cosmic enigma. Let's explore three of the most prominent ideas: the Big Freeze, the Big Crunch, and the Big Rip, and what they could mean for the ultimate destiny of everything we know. First, there's the Big Freeze, also known as the heat death scenario. Imagine the universe as a vast, ever-expanding balloon. Over trillions of years, galaxies will drift farther apart, stars will burn out, and the energy that fuels cosmic activity will slowly dissipate. The universe will grow colder and darker, eventually reaching a state where no usable energy remains. It's a chilling vision of a universe fading into eternal stillness, where even time itself may lose meaning. On the other end of the spectrum lies the Big Crunch, a dramatic reversal of the Big Freeze. In this scenario, the universe's expansion eventually slows, halts, and then reverses. Gravity, the force that binds galaxies and stars together, would pull everything back into a single, incredibly dense point, a cosmic mirror of the Big Bang. Some scientists speculate this could trigger another Big Bang, creating a new universe in an endless cycle of expansion and contraction. It's a poetic idea, suggesting that endings might also be beginnings. Then there's the Big Rip, a more violent and unsettling possibility. Here, the universe's expansion accelerates to such an extreme rate that not even gravity can hold things together. Galaxies, stars, planets, even atoms will be torn apart as the fabric of space-time itself is ripped asunder. It's a scenario that defies our everyday understanding of reality, challenging us to grapple with the sheer scale of cosmic forces at play. Predicting the ultimate fate of the universe is no easy task. These theories rely on our current understanding of dark energy, dark matter, and the fundamental laws of physics concepts that are still shrouded in mystery. Experts caution that our knowledge is far from complete, and future discoveries could completely reshape our understanding of how the universe evolves. But one thing is certain: the journey to uncovering the truth is as awe-inspiring as the mysteries themselves. To put it into perspective, think of the universe as a grand, unfolding story. We've only just begun to read the first few pages, and the ending remains hidden in the shadows. Whether it's a slow fade, a dramatic collapse, or a catastrophic rupture, the fate of the universe reminds us of the fragility and majesty of existence. And as we continue to explore, one question lingers: what will the final chapter reveal? As we reach the end of our journey through these 22 space mysteries, one thing becomes abundantly clear: the universe is far stranger and more enigmatic than we could ever imagine. From the haunting whispers of dark matter to the mind-bending reality of black holes, each mystery challenges our understanding of the cosmos and pushes the boundaries of science. These aren't just puzzles waiting to be solved, they're invitations to explore, to question, and to dream. What makes these mysteries so significant isn't just their complexity, but the questions they force us to confront. How did the universe begin? Are we alone? What lies beyond the edge of our observable reality? These aren't just scientific inquiries, they're deeply human ones, rooted in our innate desire to understand our place in the grand tapestry of existence. And while we may not have all the answers yet, the pursuit of knowledge is what drives us forward. This is why continued exploration and scientific inquiry are so vital. Every discovery, no matter how small, adds another piece to the cosmic puzzle. Whether it's a new insight into the nature of dark energy or a breakthrough in our search for extraterrestrial life, each step brings us closer to unraveling the secrets of the universe. And who knows, the next groundbreaking revelation could come from a scientist, an astronomer, or maybe even someone watching this video right now. So, as we reflect on these mysteries, let's remember that the journey of discovery is never truly over. The universe is vast and its mysteries are endless, but that's what makes it so exhilarating. There's always more to learn, more to explore, and more to wonder about. To close, here's a thought to ponder. In a universe so immense where stars are born and die in the blink of an eye, we are but tiny specks. Yet, through our curiosity and determination, we've managed to uncover some of its deepest secrets. That's the power of humanity, our ability to look up at the stars and ask, what's out there? If this journey through space's greatest mysteries has sparked your curiosity, let's keep the conversation going. Share your thoughts in the comments below. What mystery fascinates you the most? Don't forget to subscribe for more explorations into the wonders of the cosmos. Together, let's keep reaching for the stars and uncovering the secrets of the universe. The next great discovery could be just around